What if there's a planet out there that looks like a rocky super-Earth, but is actually a giant water balloon floating in space? For years, detectives of the cosmos thought they'd found another world much like our own, just bigger. A scaled-up version of Earth, made of rock and metal. But a crucial piece of evidence didn't add up. Its density was impossibly low. Now, the James Webb Space Telescope has peered into the atmospheres of worlds like this, and it has confirmed a truth that's challenging everything we thought we knew about how planets are made. This is a story about one strange planet. It's about uncovering a completely new class of world. One that blurs the lines between rocky planets and gas giants, forcing us to ask, what else is lurking in the cosmic zoo? To really get why a water balloon planet is so revolutionary, we first need to understand the box it breaks out of. For most of history, our model of the universe was elegantly simple because we only had one example, our own solar system. We had small, dense, rocky worlds on the inside: Mercury, Venus, Earth, and Mars. These were the terrestrial planets, built from the heavy stuff that could take the heat of the young sun. Then you cross an invisible line in space called the frost line. Beyond it, it was cold enough for things like water, ammonia, and methane to freeze into ice. This is the realm of the giants. Jupiter and Saturn are colossal spheres of hydrogen and helium. They grew so huge, their gravity hoovered up vast envelopes of this primordial gas. Farther out, you find Uranus and Neptune, the ice giants, with a much higher proportion of those heavier, icy materials mixed into their atmospheres. For centuries, this was our blueprint. You get rocks, or you get gas and ice. You get small and dense, or you get huge and puffy. There wasn't much room for an in-between. When we started finding exoplanets in the 1990s, they mostly fit this pattern. They were often hot Jupiters, gas giants in strange places, but still fundamentally familiar types of planets. But as our tools got better, especially with NASA's Kepler Space Telescope, we started finding planets that just didn't fit. The galaxy, it turns out, is packed with worlds in a size range we don't have here. Planets bigger than Earth, but smaller than Neptune. We called them super-Earths and mini-Neptunes, and we now know that sub-Neptunes are the most common type of planet in our galaxy. The term super-Earth was exciting. It conjured up images of a bigger, better Earth. The going assumption was that they were just scaled-up rocky worlds. A planet 1.5 times the width of Earth? Rocky. Twice the size? Probably still rocky. It was a reasonable assumption, based on the only data we had. But the universe rarely cares for our tidy boxes. As we gathered more data, a few of these so-called super-Earths started to look strange. Their masses didn't match their sizes. They were too light for their bulk. It was like picking up what you thought was a solid bowling ball, only to find it felt as light as a beach ball. Something was fundamentally wrong with our assumptions. A mystery was brewing, and it would take the most powerful telescope ever built to begin unraveling it. Our story starts 218 light-years away in the constellation of Lyra. There, a faint red dwarf star named Kepler-138 is orbited by a planetary system that would become the epicenter of a scientific earthquake discovered by the Kepler Space Telescope using the transit method, watching for the telltale dip in starlight as a planet passes in front of its star. The system appeared to host at least 3 planets. From these transits, astronomers determined that 2 of them, Kepler-138c and d, were super-Earths. They were both over 3 times the volume of our own planet. Based on the old playbook, they were filed away as likely being big, rocky worlds. But to know for sure, you need to weigh them. That's where a second technique comes in: radial velocity. A planet's gravity makes its star wobble, and we can detect that wobble by watching the starlight shift to the blue or red end of the spectrum. The size of the wobble tells you the planet's mass. When a team led by Piaulet at the University of Montreal combined years of observations from the Hubble and Spitzer space telescopes, the Anomaly screamed out from the data. Kepler-138c and d were each about twice the mass of Earth. Now hang on. They have more than 3 times Earth's volume, but only twice its mass. If they were just scaled-up rocks, they should have been much, much heavier. Their density was incredibly low, far too low for a rocky composition. This was the moment the super-Earth paradigm cracked. As astrophysicist Bjorn Bennecke explained, we previously thought that planets that were a bit larger than Earth were big balls of metal and rock. However, we have now shown that these 2 planets are quite different in nature. So if they aren't rock, what are they? The team ran the models. What material is lighter than rock, but heavier than the hydrogen and helium of a gas giant? The most obvious candidate was water. The conclusion was stunning. For the numbers to add up, a huge fraction of each planet's volume, up to half of it, had to be made of water. On Earth, water covers over 70% of the surface, but makes up a tiny fraction of our planet's total volume. On Kepler-138d, the data suggested a water layer that could be 2,000 kilometers deep. These weren't rocky planets with a bit of water. They were something else entirely. They were, for all intents and purposes, giant water balloons. The 2022 study called it the best evidence yet for a long-theorized water world. But these aren't tropical paradises. They orbit so close to their star, their temperatures are likely above the boiling point of water. Researchers predicted they'd have thick, dense atmospheres made of steam instead of an icy surface, explained Caroline Piaulet. They would harbor large water vapor envelopes beneath that steamy sky. The immense pressure could create exotic forms of water, like a supercritical fluid, a bizarre state that's neither liquid nor gas. This was a bombshell. It suggested that many of the super-Earths we've been cataloging might be water worlds. But this was still an inference based on density. No one had directly seen the water. To do that, to really crack the case, we would need a new eye on the universe. The Kepler-138 discovery was a brilliant piece of detective work, But it was still indirect evidence. Proving it required a quantum leap in technology. It required a telescope so powerful it could dissect starlight from 218 light-years away and find the chemical fingerprint of steam in a planet's atmosphere. It required the James Webb Space Telescope. JWST's superpower for this case is that it sees the universe in infrared light. Molecules in a planet's atmosphere, like water, methane, and carbon dioxide, are exceptional at absorbing specific wavelengths of infrared light. Each molecule has a unique absorption spectrum, a barcode of light that it blocks. This allows JWST to perform a technique called transmission spectroscopy with stunning precision. When a planet transits its star, a tiny bit of starlight filters through its atmosphere. If that atmosphere has water vapor, the water molecules will absorb their specific barcode of infrared light. By capturing the starlight spectrum before, during, and after the transit, astronomers can see exactly which colors of light are missing. That missing light is the smoking gun, the signature of the molecules in that planet's sky. Hubble had tried this, but its vision was limited. Distinguishing a water-rich world from a hazy hydrogen-rich one was incredibly difficult. JWST changed the game. Its advanced instruments can capture a huge range, more infrared wavelengths at high resolution, allowing scientists to take a full chemical inventory of an atmosphere. For the proposed water worlds, JWST was the ultimate judge. It could finally test the hypothesis directly. If Kepler-138d really was a steam world, JWST would see the signature of water. If it was something else, it would see that too. The theory of water worlds was finally on trial. Before turning its eye to Kepler-138d, JWST aimed at a different but similar world, K2-18b. Located about 111 light-years from Earth, it's a sub-Neptune, about 8.6 times the mass of Earth, that orbits its red dwarf star within the habitable zone, where temperatures could be just right for liquid water. This made K2-18b a prime suspect for being a Hycean world, a name blending hydrogen and ocean. This theoretical class of planet would have a global liquid water ocean under a thick, hydrogen-rich atmosphere. Early Hubble observations had even hinted at water vapor there, making it an irresistible target. When JWST's data came back, it was a watershed moment. A team led by Madhusudhan at the University of Cambridge found the atmosphere was loaded with methane and carbon dioxide. This, along with a lack of ammonia, strongly supported the Hycean world idea. It looked like the theory was correct. K2-18b was shaping up to be a true water world. But then, the case got complicated. The first twist. Despite being a supposed water world, JWST's more sensitive observations found no strong, unambiguous signature of water vapor. This was baffling. How could a planet covered in an ocean have a sky that looked so dry? One theory is a cold trap in the atmosphere, where water condenses and rains back down before it reaches the upper layers we can see. Another, more radical idea is that the surface isn't water at all, but a searing hot magma ocean. But JWST had another, even more electrifying clue. Buried in the data was a faint, tentative whisper of another molecule, dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by life, mainly marine phytoplankton. Finding it here was a staggering possibility, the first potential hint of a biosignature on an exoplanet. The scientific community buzzed with excitement and extreme caution. The initial DMS detection was not statistically definitive. It was a tantalizing clue, not proof. Later, a NASA-led reanalysis of the data confirmed the presence of methane and carbon dioxide, but found the DMS signal remained inconclusive. The dream of finding life was put on hold, pending more data. The case of K2-18b shows how science really works. A theory, Hycean world, was met with data that both supplanted it, methane, CO2, and complicated it, no clear water vapor. It then threw in a tantalizing but unproven clue, DMS. The simple idea of a water world was replaced by a more complex mystery. Some models now suggest K2-18b isn't a habitable Hycean at all, but a gas-rich mini-Neptune with a large mantle of high-pressure ice and no distinct surface. Distinguishing between a lifeless gas planet and a living ocean world has become the new frontier. What we're watching is science unfolding in real time. Old certainties are being replaced by new, more fascinating questions. If you find this journey to the frontiers of knowledge as exciting as I do, take a moment to subscribe and hit that notification bell. You won't want to miss where this investigation goes next. The complex picture from K2-18b forces us to go back to our original mystery, Kepler-138d, with a new set of questions. The simple story of a steam world is no longer enough. The universe, it seems, has more imagination than we do. First, there's the missing water vapor. If a temperate world like K2-18b can hide its water from our best telescope, what does that mean for the much hotter Kepler-138d? While you'd expect its atmosphere to be saturated with steam, complex atmospheric dynamics could mean the observable layers aren't telling the whole story. JWST won't just be looking for a yes or no on water. It'll be mapping the atmosphere's structure, looking for clues. Second, the debate over whether these are Hycean worlds or gas-rich mini-Neptunes now hangs over the entire class of planets. Could Kepler-138d just be a failed gas giant that held on to enough hydrogen and helium to appear puffy without having massive amounts of water? Teasing apart these two scenarios, a water-rich world versus a gas-rich one, is now a primary goal for JWST. The key will be in the precise ratios of different molecules. This brings us to a crucial new piece of evidence, the exoplanet GJ9827d. Located about 97 light-years away, this planet is just under twice Earth's diameter. In late 2024, astronomers announced that JWST had made an unambiguous detection of an atmosphere saturated with water vapor. The data indicates it isn't a hydrogen world with a little water, but a world with a steam-based atmosphere. This was hailed as the first observational proof that steam worlds really exist. GJ 9827d is incredibly hot, around 427 degrees Celsius, 800 Fahrenheit, making it more of a celestial pressure cooker. Its existence proves that planets can have atmospheres dominated by heavy molecules like water, confirming that this category on our planetary checklist is real. GJ 9827d gives us a vital anchor point. It shows us what a true hot steam world looks like to JWST. Now, when Webb eventually turns to Kepler-138d, scientists can make a direct comparison. Does its spectrum look like the steam-drenched sky of GJ 9827d? Or does it look more like the methane-rich atmosphere of K2-18b? The answer will help us build a family tree for this bizarre new class of planets. These discoveries are doing more than just adding specimens to our cosmic zoo. They're forcing us to redraw the map of the cosmos. The line between rocky and gaseous has been irrevocably blurred. The term super-Earth has become almost meaningless without asking, is it a rocky super-Earth or a water-rich sub-Neptune? This challenges our theories of planet formation. How do you build a planet that's 50% water? One idea is that they are failed ice giants. A planet forms far from its star where ice is plentiful, building a huge core of rock and ice. But if it fails to pull in enough hydrogen and helium to become a Jupiter, it might remain a massive icy body that then migrates inward, where the star's heat transforms it into a water world. Another fascinating theory, supported by recent experiments, suggests planets can make their own water. If a young, molten planet has a primordial atmosphere rich in hydrogen, that hydrogen can react with oxides in the planet's magma ocean to create enormous quantities of water from scratch. This could allow water worlds to form much closer to their stars than we ever thought possible. These new pathways have huge implications for the search for life. For decades, we focused on Earth-like rocky planets, but the discovery of potential Hycean worlds like K2-18b blows the search wide open. These water-covered worlds could offer a completely different but viable path to life. And because their thick atmospheres are easier to observe, finding evidence of life on them might actually be easier than on a smaller, rockier world. The James Webb Space Telescope is at the heart of this revolution. It's providing the chemical data needed to test these competing theories. By analyzing the atmospheres of more and more of these sub-Neptunes, we can compare hot steam worlds like GJ 9827d to temperate candidates like K2-18b and piece together their origins. The age of simple categorization is over. We're now in the age of planetary characterization, where every new world gives us a deeper understanding of the universe's incredible diversity. We began with a simple idea, a giant water balloon in space. We thought we found it in the Kepler-138 system, where planets that should have been solid rock were impossibly light. But as this investigation has shown, the universe is never that simple. Our journey took us to K2-18b, a world that promised to be an ocean paradise, but instead delivered a scientific puzzle box. Rich in some building blocks of life, but with a mysteriously dry-looking sky and a tantalizing, unconfirmed hint of a biosignature. Then we visited GJ-9827d, a scorching steam world that proves such planets are not just theoretical, but real objects that JWST can see and study. What we've uncovered is not a single oddball, but an entire new branch on the planetary family tree. The story of the water balloon is the story of how one anomaly can shatter a scientific paradigm. It has forced us to accept that our solar system may not be the standard, but just one possible outcome. The most common planets in the galaxy are not like Earth or Jupiter. They are these strange, in-between worlds. We are standing at the very beginning of this new chapter. JWST has given us the tools to not just find these planets, but to know them. And as we look deeper, a profound question hangs in the air. If there are this many worlds with this much water, from temperate oceans to superheated steam, does the probability of life existing somewhere out there go up? What if the best places to look for life aren't Earth-like planets at all, but these bizarre, abundant water worlds that are only now swimming into view? The quest to answer that question is just getting started. If you want to follow along as we explore more strange new worlds, be sure to subscribe and check out this other video on another one of JWST's most shocking discoveries. As always, thank you for watching and keep looking up.